I wanted to quickly start with showing. So the reason I have this presentation right now is to mainly show you a tutorial on how to use the live star catalog, and that's so that you can understand how it was done. You could reproduce it, but you can also start to create your own catalogs using the live database for your own projects. And to do that, I want to show you some of the tools we have now available. One of them is we have a live target database read the docs webpage. I can quickly put the link in the chat. One moment. And if you go there, we have different things here, contact, attribution, stuff like that. We have also installation of basically everything is here. So you can reproduce everything, the database, the catalog, and so on. But I want to start with the introduction because we found out there's some confusions around what kind of target samples we have actually in life. So I just quickly want to have a look at the different ones that I'm aware of. So we first have this target database, which the goal is to just get as much data on the potential targets for life as possible. We have 30 parsec cutoff. We have not only stars, but we have system, planets, disks, and so on. And the only thing we cut out here are single brown dwarfs or white dwarfs. But other than that, we have all stars within 30 parsec. Then we have of order of 10 to the 4 of object in here. And then the next thing is like the star cat that I want to go in detail today. And that's just as much as is needed for the life sim, where you can simulate what life would return. And there we take from the database, we only take mature single stars and white binaries. White binaries means they have stable planetary orbits, potential orbits in the habitable zone. And it's only stars, there's no planets and so on in there, and it's 10 to the 3 of order of magnitude. And then this gets fed into the life sim. Life sim does some simulations according to different scenarios, different signal to noise, and so on. And then you get out a list of the stars with the highest simulated observation yield. So those simulated planets where you would find the most planets, and you get like 100 stars in this list. And then there's an other list that people have been working on for life. It's the golden targets. That's where you already know, like, this star looks super promising, like Proxima. You would want to look with life at Proxima just because it's close enough that you can do lots of stuff with it. Or you have some stars that get observed with HWO, then you might want to look at it as well. Or you have some stars where you already know we have nice planets there in the habitable zone. So those are the golden targets, the ones that we are really sure we want to look at. And they are about 10-ish targets. And then in the end, the final target sample is those golden targets plus some of those stars that come out of the life sim output. So I hope that gave a little bit of an overview of what kind of samples are around. And I want to go into this one here a bit more in detail. Of course, I will also touch on the target database because the star catalog feeds from the database. So the cool thing we have here is we have tutorials. So you can go there, there's Jupyter Notebook tutorials. You have something like, how do you access the target database? You have like Topcat would be one option. I think also in the science team meeting some years ago introduced, but the easier one is using Python. The only thing you need to install is PyVO. And then you could just run this short script here and you would get output. And here, that was just an example query. We have different other example queries. For those people who are not so used to ADQL, they can just look, oh, I want children of an object, or if you go to the lower bottom, there's like, oh, that's a query we do for the live star catalog before we processed the list that we got there. So that's just some example queries if you're not sure what to ask the database, what kind of data it should return. And the cool thing, if you go back to the tutorial, is you can directly download it. So the StarCat here you could download. I just did that a moment ago just to make sure that it works. Then you get this Jupyter notebook. And let me see if it really works here. So I activated my environment that has the Python PyVO module in here. So let's see if that's really everything I need. And yes, of course, you need to have installed Jupyter Notebook so that you can use it, I think at least. Good. So I click on this notebook that I just downloaded from this web page. And then we have the whole from start to the bottom in the end where you get out the live star catalog. It's called 4 because it's the 4th version, but that's kind of the one that you can directly access from the database. And it has the line of code. You can just run it. Actually, it looks like I also need NumPy and AstroPy. Interesting. The other one, for the other example, like the just live target database access, there you only need Python virtual observatory module. But if you really want to do the star catalog, you need to kind of reformat the stuff a bit, and for that you need some table tools. Okay, you can use some stuff if you, well, most of the time you don't do this. This is just if you really downloaded everything that I coded, but you can, we can just start doing like the modules, importing them. I won't do this one because that's really if you have downloaded more than just those modules, and then it's just 2 functions that I copy pasted out of my code. It's the same thing that would come here, but I just made one that queries the database. It looks a bit more complicated, but it's actually exactly the same we had back here, which is just a few lines saying, this is my query, this is the link where the database is published. Please do get it back and make it nicely into a table, and then is what you get out. So that way you have a bit of pre-programmed functions, and afterwards it leads you straight through the whole construction process with also motivation why we do what. Like we start with a 30 parsec distance cut. We write the query, which is, as I said, you can just have it online as well. Here, it looks complicated. It mainly says, hey, go to the distance of 30 parsec, take only the stars, and then everything else here is all the parameters you want. So you have here the name of the star, you have the right ascension, the declination, parallax, and so on. And let me get back here. So this is all the query that you ask the database. Did I run this? Let's just make sure I run this. And then we query the database and we get out a list of about 10,000 stars. But that's not the end result that we want, because as I said, we want white binaries where we test where the planet orbits are stable. We also want to remove stars that are not main sequence. So for that, I have here 2 lines of code that just only keep the ones in spectral types, these ones here, and only keep the ones in luminosity class main sequence. And then there's, because I still had an error in my version of the database that's currently the stable one published, there's this one that says only keep the ones where we really have mass values. So throw out the ones that where we don't have those, which is like 27. That's just a bug that I have in the database that is fixed already, but it's not published yet in the database. Oh, this one's outdated. Interesting. So as I said, still a bit work in progress, but actually it's now at the status where you can access it, where you can use it for your own projects. That's why I do now a presentation about it. But I just realized, because I had here a note written down, that actually it's a bit outdated. Should still work, is all the same result, is just nicer commented in the newer version. Then we split it up into single stars and multiple stars. As I said, with the multiple stars, we need to have a bit more look in there. We only want binaries. We don't want higher order multiples. We only want the ones that have nice separated from each other. So it all looks a bit difficult, but that's why I have all the comments around it explaining. We also want only those where we have separation measurements that we get from the Washington Double Stars catalog. And in the end, we have about 500 binaries, and then we do the white binary criterion from, how was it called? Wiegert, Holman and Wiegert from 1999. This is a criterion that just computes if the orbits are stable, and I assume here I make some assumptions here, like eccentricity being that it's circular orbits and so on. But in the end, so I could just run it all. In the end, what you get out is the final star catalog, where I merge again the singles and the final ones from the multiples. And then there's just 2 blocks of code. That's an additional thing where we can look at architecture of the live mission. So that's just an example, like in case we can't look at the whole sky with live, we might not get some angle from the ecliptic plane. So I included here, let's just use an example angle of 45 degrees on top of the ecliptic plane and below the ecliptic plane, and then add a flag that says this one is within this area or it isn't, this star. And that's just something I want to do a bit more on in the future, but it's just kind of an example how you can use the catalog to then do some architecture trade-off studies. Is it worth having a bigger area where we can observe the stars because we then have more stars, or is it that too costly for the technology and instrumentation team? Yes, and in the end, that's the only thing where you really need to get one of the modules that I have in my code. As I said, I have here an installation guide how you would get them. That's just to have a nice plot. So quickly explaining this plot, we have spectral types here, and we have the number of stars, and we see in life we're mostly interested in the FGK stars because they are sun-like stars, and we see, well, in 30 parsec we have maybe 100 of those, and including like binaries. And then we look, okay, which of those are actually close? So we have now distance spins of within 5 parsec. We only have M stars, that's those. Then from 5 to 10 parsec, we have a few K stars. 10 to 15 parsec, there we get some other stars. Some of those we really want. And as you can see, most of the stars are as expected in the farthest away distance spins. Yes, I think it sounded a bit, I was talking a bit fast. Let me see if I wanted to say something else. Yes, a quick outlook. So currently we're working on a research note for the Astrophysical Journal in my work group, and it looks quite good. Still needs a few weeks of working on, but that should be something we have published where one can read a bit up, but its intent is mostly to point you again to the different resources we have online and the motivation why we did it. Oh, I was perfectly in 15 minutes, so any questions?